Welcome back. Let's get back into our discussion on normal distributions. But first, we need to finish our discussion on uniform distributions. So remember for me that a uniform distribution was anything where all of your outcomes were equally likely or pretty much equally likely. That's what we had here with the births by month. And you can either forcefully do that just by saying, oh, yeah, it looks to be about the same, and just averaging it out and just having everything with an equal likelihood. In fact, if, let's see, there's 12 months here in the year. So you could say that the probability of being born in a given month is 1 in 12. Interestingly enough, this red bar is about that same height. It's a little higher because I did add some randomness to these numbers. But the fact remains that it should be about 1 in 12 for a uniform distribution. Well, what if we are continuous, where instead of having 1, 2, 3, or 12 discrete outcomes, such as January through December, instead we allow for any outcome, specifically any amount of time between 0 and 300 seconds. Now, that doesn't mean there's 301 distinct outcomes, right? I'm saying anything between 0 and 300. So sure, 0, 1, 2, 3, 4, up to 299, 300. Yes, those are all allowable outcomes. But so is 187.63. So is pi. So is 349. Oh, no, sorry, not that one. 249.712836, right? Those are all different allowable outcomes. So there are infinitely many allowable outcomes for that range, but they're all equally likely. Same too for any temperature between absolute 0 and 1000 degrees Celsius. Sure, we all would know that that's 1,473 degrees Celsius is the range there, but there are infinitely many values that you could fall in for each of those. Same for heights, right? You could be 100.2 centimeters tall, and that would be in the range between 100 and 200 centimeters. So we're going to have our range of allowed values, and then what we're going to do for a uniform distribution is assume that every outcome is equally likely. Now, normally, and you'll have to forgive the pun there, normally that doesn't happen. But for uniform distributions, it does. And obviously, there's a lot of things you can think of that is not going to be representable with with a uniform distribution. But there are a few things that are. And of course, if nothing else, uniform distributions are such that the arithmetic is pretty easy to carry out. So it's a good starting place. For instance, suppose that you're waiting in line at Burger House and you know, for however reason, that the wait time is somewhere between 0 and 350 seconds. And you want to know, how likely would you be to wait at least 3 minutes before being served? Now, we can ask the same question again in the future with a normal distribution. But right now, just the way it is, let's assume a uniform distribution, that you are equally likely to wait 2 seconds as you are to wait 302 seconds. So let's take a look at what that kind of distribution will do for us here. So what I have for us is a uniform distribution, not normal. Quite the opposite, really. And what I'm doing here is I'm showing you how likely each thing is, each amount of time you wait is, given your total range. And I want you to notice something. If we have just a width or a range of 1 minute, then it's a very high probability right there. But the farther out you go, the less probable it gets minute by minute. And that makes sense, right? To a certain extent, that makes sense. The further out we go, everything still being equally likely, the less likely in turn that a single spot will be. So let me put it to you this way, and then we'll pick up with this in the next video, because I have 12 seconds. How likely would it be that if this range is almost 6 minutes, that I have to wait at least 3? We'll take it there.